participate in this occasion of Larry being awarded this recognition. It certainly is rightfully deserved. And once again, thank you very much for inviting me to be a participant in this symposium today. As I think about Larry's success, I think of it largely drawing from two sources, of course, leaving Rena out of the discussion. And on the one hand, his exquisite and creative knowledge that's been employed to build these fabulous, sophisticated instruments, on the one hand, and then the other bit, which I think has led to Larry's success, is also his really very deep and fundamental understanding of matter-radiation interactions. And it's the combination of the two, I think, that has led to the beautiful summary of work that you described for us. So it's to honor the second value in particular that I'm going to give this talk today about some results from a couple of years ago and from a couple of weeks ago that have to do with developing small molecules as probes, essentially, of complex biological systems. And the initial motivation for this work actually grew out of a conversation that I had with a colleague of mine in the physics department who asked me if we could somehow exploit ultrafast infrared spectroscopy to be a probe that we can use to help understand generalized anesthetics. This is still an unresolved problem. And, of course, there are a wide variety of molecules that act as agents for anesthetic effects. I've just summarized a handful here. And, of course, there's a wide range of molecules, and that's why it's such an intriguing problem. Notice, by the way, nitrous oxide is listed here, laughing gas, as you probably know. And this problem of generalized anesthetics actually has a very long history. It was known for more than 100 years ago that the potency of different anesthetics is correlated with their solubility in olive oil. Olive oil has this triolein as a major component. Of course, you can see that looks very much like a lipid molecule with its head groups and its tails. And so this led to the development of a theory about generalized anesthetics that was based on phospholipids. So that was our original motivation for this work. And in fact, I have learned nothing about the mechanism of generalized anesthetics, at least up to this point. But what the work led us to do is try to develop this molecule, nitrous oxide, as a probe of phospholipid model environments and with an eye towards ultimately employing this methodology for learning about other biological scaffolds, complex systems such as proteins and nucleic acids. N2O really is a fabulous IR probe. It's got a number of attributes for use in this context. It's a small neutral linear molecule, and that, of course, makes it attractive for putting it into complex systems because it doesn't have a charge, it's not very big, so it's not terribly perturbing of the system. It has a vibrational frequency which is quite sensitive to its local environment due to the resonant structures that, our freshmen would be able to draw for the ground electronic state character. It's got a IR absorption associated with the asymmetric stretch, nu3 mode, which is at around 22 in the gas phase, solvent dependent. But the nice attribute about that particular resonance is that it's in a region of transparency for most biological systems. It's got a strong absorption, the nu3, the asymmetric mode. And then probably most important, I think, it's got a wimpy dipole, 0.16, and so consequently it can find itself in both polar and nonpolar environments. So in a given experiment, you can probe a variety of polarities, which of course is crucial for biological systems, again, such as phospholipids, proteins, nucleic acids. So the particular experimental system that we set out to look at in terms of a model system is N2O in solvated DOPC bilayers in particular, which are spontaneously formed at room temperature. DOPC is a zwitterionic phospholipid. It's got, these charges in its head group. It's 18 carbons long in terms of its acyl chains, and these are a picture of the structures, the bilayer structures that form. Here you see the acyl chains. The red are the head groups, and then you get these regions of what I'll call interlamellar water. These are, in fact, I'll refer to as biological waters. As you first start to hydrate the lipid system, the waters, of course, accumulate in this interlamellar region. And as you continue to hydrate, the layer swells until it reaches a point where you can't absorb any more into that region. And as you continue to hydrate the system, then you reach beyond this excess water point. You create pools of bulk-like water. The excess water point, just to try to give you some sense of the numbers of molecules that we're talking about, the excess water point for DOPC is 28 waters per lipid. Okay, that's about 39% water by weight. So the idea was, well, can we possibly use ultrafast spectroscopy to learn something about the structure and perhaps dynamics of this nano-confined interfacial biological waters using as I said, ultrafast IR technique. So our first attempt was with pump probe spectroscopy. Stepping back one bit further from the phospholipid system, we first started to look at model systems for the phospholipid, and that's just looking at the characteristics of our probe molecule, that's N2O, in neat water and octanol. Water, obviously thinking of the interlamellar regions, something to contrast with, and octanol as a species which has acyl-like chains. And these are the corresponding absorption spectra for N2O. It has a peak frequency in water of 2230 and a peak frequency in octanol of 2218, so nicely separated. And we were just going to initially proceed by looking at pump probe measurements using pulses on the order of 100 femtoseconds to begin with. And so the question is, can the rates of vibrational energy relaxation in these two different environments, that's to say something related to the inverse of their lifetime, somehow be a measure of the local environment and contrasting polar and nonpolar regions? So, of course, the way a pump probe experiment is carried out, we initially excite our sample with an ultrafast pulse that is coincident with the fundamental transition, the 0 to 1 transition. And then sometime later, we probe the system and look for the signatures of the return of the system to equilibrium. There are two types of signatures. There'll be an absorption-like feature, which is associated with the 1 to 2 transition. Because every time we're looking at ultrafast spectroscopy in the infrared, it's immediately a 3-level system because of the near harmonicity of the system. So we have an absorption-like feature, and then, of course, we also have a bleach-like feature. And both of these will be capturing the dynamics of the excited vibrational level. So as I dispersed the probe pulse, this is the signal that one sees for N2O in octanol and N2O in water. You can see the bleach and absorptive-like features, which, of course, are displaced by the anharmonicity of the 0 to 1 and the 1 to 2 transitions. Right? The 1 to 2 transition being red-shifted, obviously. And correspondingly, you see the absorption and bleach-like feature for the N2O in water. And the striking thing that one sees, despite the similarity of those absorption bands in these neat solvents, is that the rate of vibrational energy relaxation is drastically different. It's about 52 picoseconds in octanol and about 9 picoseconds in water. So certainly there's something about the rates of vibrational energy relaxation that is very different in these two kinds of environments. Once again, these just showing the nice exponential decays. However, there's, in addition to this big difference in the rates of vibrational energy relaxation in these two systems, there also was another feature that showed up in the water response, and that is the decay of the 9 picosecond signal that one saw ended up with a plateau. And in fact, this plateau extended out as far as our translation stages would go, several nanoseconds, and extends out much longer than that. It recovers within a millisecond. And so the question was, curiously, what is that about? If we took out the N2O, then in fact what we discovered is that indeed we had a response just in neat water. I'm just showing the dispersed response now in neat water. This is the frequency of our pulse, right? You have a short pulse, you have a lot of frequencies, a bandwidth of a couple hundred wave numbers, and this is time. Now, it's hard to see the time axis, I apologize, but the decay of this signal, this bleach that's showing up, is happening very fast. It reaches this plateau in about a picosecond. And then you get this very slow millisecond decay and a return to equilibrium. So what is that about? Because here we are at 2200, 2250 roughly in water. And the answer is, here is the linear spectrum of water. So, here's the famous stretches, and here's the famous bend of water. And so nominally we think of water as being transparent at all other regions. But of course, let's put this absorption spectrum on a semi-log plot. Semi-log plots are great. They have, there's so much information in the semi-log plot. And of course, what you see right in this region where the N2O is absorbing, there's another feature that shows up much more clearly in the semi-log plot. In fact, it's the third most apparent feature in that water spectrum, and that corresponds to the bend plus libration band. So it's a combination band that's sitting right in this region. It's quite broad. It's centered at about 2150. And so what we were looking at, this signal, this very rapid picosecond decay and slow relaxation is associated with absorption into this combination band. Let me also point out that I haven't offset this spectrum. And so formally you can see, aside from these discrete, albeit broad bands that you see in this semi-log plot, there's also a continuum of states of water in this absorption spectrum, a density, a spectral density, if you will, that's underlying this absorption spectrum. And that's really crucial. In fact, the way I come to think about water, I think of water as being quite black, quite frankly, and it's got this density of states extending out, in fact, up into the visible. And, that's quite crucial for chemists because energy is flowing into water for a chemical reactivity that takes place in aqueous environments. Okay. As you might imagine, there's a lot of work that's been done on energy relaxation in water. None, of course, in this bend plus libration combination band region. I won't spend any time on talking about the mechanism of vibrational energy relaxation in water, except to say we worked out the simplest model that we possibly could to model the kinetics that we saw, and also to incorporate all the knowledge about energy relaxation in water. And this, in fact, was the simplest model that we could come up with. And I'll just simply highlight the main point, which is that as one excites into this directly into this bend plus libration mode, that the energy in a concerted way decays into the bend of water plus the low frequency thermally excited modes of water. These are modes that are associated with that contribute to the continuum, that are the combinations, overtones of low-frequency modes, intermolecular. Okay, back to the DOPC water. Here's a FTIR spectrum of N2O in DOPC. Right? Now that we've done these two model environments, let's go back to the phospholipid. And of course, here you see for 20% hydrated DOPC, this is the absorption of N2O that is located in the acyl chain region, and here is an absorption feature, just a shoulder here on the absorption that corresponds to water that's in the interlamellar, interfacial, nanoconfined area of these phospholipid bilayers. Okay. So then we performed pump probe measurements, as you see here, and we dispersed them, and you see the absorptive-like and bleach-like components of the response. And the way we get information out of these signals is then to globally fit them with a formalism of this type, where each particular dispersed frequency is assigned a minimum number of decay components to figure out what species, in fact, are contributing to the dynamics, to the decays that we see there. And in that fashion, then, we generate decay-associated spectra, each characterized by its own decay timescale. And we're only going to be looking at the bleach side to avoid interference with overlapping absorption signals. So here's an example of what we see in it, analyzing the pump probe spectrum that's dispersed in N2O and hydrated DOPC layer, 20% hydration. Again, to give it some feeling in terms of molecules, this is roughly 11 waters per lipid. Okay? And what we find, probably not surprising, is that there are two components, this red component and this blue component, that contribute to the observed response. The red component decays with a timescale of 52 picoseconds, just nearly identical to what we see in octanol. And so, of course, we attribute that to N2O that is in the acyl chain region of these phospholipids. The other portion of the signal that we can decompose has a frequency that's near the water absorption frequency, 20 to 30, and has a 29 picosecond lifetime. So the frequency is right. You know, again, this is all, we're not putting in any parameters. This is what comes back at us. So the frequency is right and corresponds to what the force constant looks like in water for N2O. However, the rate of vibrational energy relaxation, you see, is very different than what it is in bulk water. Right? It's a factor of, 3 times slower. So a significant effect. And then, of course, we can carry this out for a number of hydration levels. Here's results for 10% and 33%. And again, we find two components for the decay. One always centered at the acyl chain region, or the hydrophobic region, on the order of 50 picoseconds, and then the other one centered around water. But it has a different lifetime, different rate of vibrational energy relaxation depending upon what the level of hydration is. When we go beyond the excess water point, so this is now 50% of hydration by weight, 44 waters per molecule, what we find, interestingly, is that we need a third component to fit the observed responses. That again, we see at 2218, something that has a lifetime of 51 picoseconds. You see a component around 2230 that's got a 20 picosecond lifetime. And sure enough, at this point where we're above the excess water point, we see a third component that has a lifetime of 9 picoseconds in the water region. And that's, of course, consistent with the formation of these pools of bulk water. Okay, so there are two very different types of aqueous environments is what we're finding once you get above this excess water point. So here I'm just summarizing the information for this lifetime or vibrational energy relaxation set of experiments in phospholipids as a function of hydration level. Right? So hydration is increasing here. And what you find is that for N2Os that are in the acyl chain region, the lifetime is, of course, independent of hydration, as you might expect, and has a lifetime of 52 picoseconds or so. For the waters, for the N2O that's dissolved in the interfacial waters, you find that as the level of hydration increases, that the rate of vibrational energy transfer increases. So it's quite slow. It has the longest lifetime where the number of waters is the fewest. As you begin to add water, the lifetime begins to get smaller, beginning to approach the bulk water. But once you reach the saturated level, of course, it doesn't change anymore, and you get evidence then of the bulk water showing up. Okay. So what's this about? What's this telling me? Well, just phenomenologically, it certainly is indicative that these lifetimes are becoming some probe of interfacial water structure. And just to make that a little bit more concrete, we perform MD simulations on an infinitely dilute phospholipid. So imagine this is the object that I'm describing here. Here are the tails facing one another, the head groups, and there are the waters, right? And what I'm showing here in this table, well, first let's say the location of the waters of the black line. So there are no waters, of course, in the region where the acyl chains are. You get waters, of course, in the region of the head group, obviously, and then for infinite dilution further on out. Okay. The red line just indicates where the head group is. That's the location of the phosphate group in the head group of the phospholipid. And what we're calculating down below here is the polarization of the system. And so you notice that for waters that are in the region of the head group, you have a highly ordered structure. This is very different than, of course, what you see in the bulk water region. The waters, in other words, are oriented. And, of course, the opposite signs just reflect the fact that the waters are oriented towards these bilayers in the opposite sense. In fact, interestingly, it's the protons of the waters that are very much liking the negative charge in the phosphate groups. That's what's exposed. And so what you've got in the region, these intermolecular regions of relatively low number of waters, you get a large percentage of these highly ordered waters that's very distinct than the bulk water. In other words, the hydrogen bonding network of the bulk water, it's no one's surprise, I suppose, of course, is very much disturbed, perturbed by the head groups of the phospholipid. Okay, so how does that manifest itself in the dynamics that we're seeing? So let me suggest the following, and this is my hypothesis for this. What I'm showing you here are the IR spectral densities, in other words, the water spectra, excuse me, the spectra of water in these hydrated DOPC systems. And I've normalized by the number of waters in the system. So these spectra are not displaced in order to view clarity. These are truly what the spectra are. And I'm showing these as a function of hydration. So this is our lowest hydration level, 10%, 20%, 33%. Once you get to this point and, in fact, the region where you get excess waters, you're not getting a big change in the appearance of this spectrum. Okay? And so the point that you can notice, just even in a phenomenological way, is that at the lowest hydration level, the ratio of the spectral density, so to speak, that is located at the resonance of the N2O transition is much more heavily weighted in terms of the combination band. Thus, the contribution of the continuum at that point is relatively small. For higher levels of hydration, in fact, the intensity of the combination band itself has virtually unchanged as a function of hydration. But the biggest difference is in the overall intensity that's associated with this continuum region. Okay? So it's the size of the continuum and not the combination band that is changing as a function of hydration for these biological waters. So what I'm plotting here is the absorption intensity that's associated with the combination band. Combination band alone is a function of number of waters or hydration level, in other words. And that doesn't change much, as I just showed you. On the other hand, this is the combination of the continuum level as a function of the number of waters. And that, of course, is extremely dependent on hydration level. And you see the really high degree of correlation that there is between the intensity of the continuum that's resonant with the N2O frequency and the rates of vibrational energy relaxation. These are really strongly correlated. And so what's going on? Well, in the hydrated lipids, you have this disturbed hydrogen bonding structure. These are highly oriented waters, and that's affecting the density of states that are resonant with that particular transition frequency. Our probe is this nu3 band of N2O. And so just in a Fermi golden rule way, which is written here, because the density of states is changing as a result of the change in the structure of the water, the rates of energy transfer, in other words, the lifetimes that we're probing, are changing. And that's what accounts for this hydration level dependence in these interfacial waters. Okay? So the lifetime has really become a measure of the structural changes relative to bulk water for waters in interfacial and nanoconfined regions. Okay, and there's a number of other nanoconfined systems that we've looked at, all behave the same way. Well, this is satisfying to see this correlation between the orientation of waters and the lifetime. These lifetimes are not a direct measure of anything physical. In other words, to take these numbers, these rates of energy relaxation, and to learn a little bit more about the system, one needs to employ simulations or other theoretical methods. But there are other ultrafast techniques that can more directly report on motions of the solvent environment and provide perhaps a more quantitative description of what a local environment looks like. And so let me also tell you about our recent experiments using 3-pulse photon echoes in the infrared to learn about the structure and dynamics of solvated regions. And this is still in its beginning stages, so what I will tell you about is N2O in water and octanol. Same reporter molecule and same model systems. In a 3-pulse photon echo experiment, and we're going to be carrying out a dispersed 3-pulse photon echo, it's the vibrational transition of the solute that really is, once again, a reporter, but perhaps here in a more direct fashion, of the inherent motions of the solute on a femtosecond to picosecond timescale. So, we're learning about the process of solvation. And what we talk about is solvation, it also is spectroscopy. It's giving rise to the line shapes that one sees in absorption. And so, again, to give this a little bit of a picture, here's our transition frequency. In this case, that's associated with the N2O asymmetric nu3 mode. And, of course, due to the inherent fluctuations of its solvent, we're not in a crystal, and these may be changes in density, and there are electrostatic interactions between the solute and the solvent, which then, of course, affect the force constant, which changes the frequency that you see. So it's this sense that our reporter molecule is going to be telling us about the inherent motions of the system that it's immediately in contact with. As a result of these solute-solvent interactions, of course, as I'm describing, you get fluctuations in the transition frequency, right? and these are going to be capturing information about the amplitudes and the timescales of the inherent motions of the local solvent environment. So once again, here's the absorption spectrum of N2O in water and octanol. And we've already spoken about their different frequencies. And their widths are not so different either, that they're 10 wave numbers and 12 wave numbers. So they're not very different. And of course, the dynamics that I'm talking about are the dynamics that account for the breadths that you see in these spectral features. The key quantity that one determines by a 3-pulse photon echo experiment is a transition energy correlation function. I'm just going to call it C of T. And it formally has this definition, and it tells us about the timescales of fluctuations for the transition frequency. What's typically done is to treat the transition correlation energy function in terms of a Kubo formalism. And that's to say, and which I've outlined here, and that's to say that for each degree of freedom, and that's the summation here, for each degree of freedom that couples to changes in the transition frequency, we characterize those fluctuations by two parameters. One is delta, and that's associated with the instantaneous Gaussian distribution of transition frequencies. So in other words, you have a solute and a solvent. It's a liquid, of course, undergoing its fluctuations. And at a given instant, if you take an instant, you would have a distribution of transition frequencies. And that's outlined by this blue line here. Okay. In the Kubo formalism, by the way, that distribution is a Gaussian, and it's an interesting question to ask and explore whether that's the right distribution. But nonetheless, we'll just characterize this as a Gaussian, and delta will characterize our instantaneous width. And then the other parameter that goes into this formalism, oh my, is the fluctuation timescale, tau. And that accounts for the transitions moving towards the mean, and that results in the phenomenon of line narrowing. So this experiment is carried out, as I said, with 3 pulses. There are 2 time delays, the coherence time and the population time, and one generates a signal in a phase-matched direction that is in a dark direction in this particular experiment. There are a number of histories in density metric space that contribute to these signals. Let me just say, and my point of showing this is, as long as I have pulses such that I know which is the first and which is the second temporally, as long as pulse number 1 precedes pulse number 2, only these diagrams at the top contribute. And I simply show this here to outline the fact that the polarization that's generated for these 2 pathways will be at the fundamental frequency, and for these 2 frequencies, the signal polarizations that's generated is redshifted due to the anharmonicity. And by virtue of the transition moment dependence in quantum numbers, those should be 1-to-1 in intensity, even though there's 2-to-1 in pathways. And so what you would expect when you disperse these signals, which is what we're doing, is you'd have 2 lumps in these responses. This is the dispersed frequency. This is the variable tau for a given population time. So this is the ground state contribution. This is the 1-to-2 contribution, and they're virtually 1-to-1 as it should be. For octanol, they're not, and for reasons that I know and I don't have time to tell you about. But nonetheless, this is the signal that we observe for the portion of the signal that's just integrated over the response, which helps us get rid of water interference, and we can fit this and determine energy correlation functions. So this is over here the energy correlations that are determined by the dispersed 3-pulse photon echo experiments, and they're really very different. They're dramatically different for octanol and water. For water, it's all over in about 3 picoseconds or less. For octanol, it extends out to about 100 picoseconds. So what is that all about? Well, this is what we find fitting these experimentally determined energy correlation functions. For N2O in water, the correlation function has a very rapid component. This is really well known from all 3-pulse photon echo experiments. This rapid response is due to the inertial motion of the solvent. And then the other component with the 1.5 picosecond decay has to do with the hydrogen bond making and breaking times in water. That's well established at timescale. We find it. That makes perfect sense. In octanol, there's not two components, there's three components. Again, there's this inertial component, one always sees. It has to be a little bit slower, which makes sense. And then we see a decay at 3.3 picoseconds, and then one component that's 35 picoseconds. Again, the 3.3 picosecond decay is perfectly expected. That's a timescale that's associated with hydrogen bond breaking and forming. That timescale is known from other experiments with other alcohols, from simulations. And then the other component that's long, which is entirely inhomogeneously broadened at 35 picoseconds, is the motion of the acyl chains of the octanol, and that is known from simulation. So just, okay, I'm just finishing. Here, this is a lovely snapshot from simulation that I'm citing here by Peter Coleman. The blue balls that you see here are the van der Waals radii of oxygens in octanol, and the red, which are somewhat hidden, are the van der Waals radii of the hydrogens of the OHs, in other words, the hydrogen bonding. And so it's the making, and you get lots of clusters, that's what you see. So it's the making and breaking in the room temperature solution of those bonds. It's the 1.5 picosecond dynamics that's causing the reporter's molecule, the N2O, to fluctuate. And it's the squiggly lines, which are the acyl chains. It's the motion of these guys that correspond to the 35 picosecond decays. So let me just conclude by saying, I think that this is a nice technique using N2O and ultrafast vibrational spectroscopy to learn about structure and dynamics, not only in interfacial waters, but also in nonpolar regions and other biological systems. Of course, we're going to apply this to lipids and proteins and nucleic acids. It's actually a better probe than other choices that have been used by other people. It's not charged, etc. And with that, I just want to acknowledge the people that I've worked with and also the funding sources, and I thank you for your attention.